Welcome to UO Today. I'm Paul Peppis, Director of the Oregon Humanities Center. My guest today is Janna Levin, Professor of Physics and Astronomy at Barnard College of Columbia University. Levin's research concerns the early universe, chaos, and black holes. She's interested in the topology of the universe and whether it is infinite, and she has contributed to an understanding of the cosmology of extra dimensions and gravitational waves in the shape of space-time. Levin is the author of the popular science book, How the Universe Got Its Spots, Diary of a Finite Time in a Finite Universe, a Finite Space. Her second book, a novel, A Madman Dreams of Turing Machines, won the Penn Bingham Fellowship for Writers. On February 19, 2015, Levin gave a talk, From the Big Bang to Black Holes, Time, the Universe, and Everything, as the Oregon Humanities Center's 2014-15 Cressman Lecture. Her lecture was part of the Connection series. Thank you, Janna, for coming on the show.
Thank you for having me.
You hold a PhD in theoretical physics. What is theoretical physics?
So theoretical physics is an attempt to understand everything that we can about the universe in terms of its simplest mathematical laws. And in principle, theoretical physicists tend to imagine that everything we could possibly conceive of reduces to these fundamental laws at some stage, so that it's ultimately really a theory of everything. And people use that expression, theory of everything, really to mean the idea that we're going to write down one mathematical sentence that describes not only all the laws of physics, but everything else that happens once the universe is created.
So this theory of everything, is this?
You laugh, you think I'm joking.
No, I never laugh. Is that gonna be realized, that theory? There isn't a theory of everything yet.
There isn't, but it's amazing how far we've marched towards that theory of everything. So we used to think electricity was something different than magnetism. You know, magnets that you find even in nature versus the thing we use to flick the light switch. We think that those are two different things. Obviously, by the time we flicked light switches, we understood this, that they're actually different sides of the same coin, that they're unified into one fundamental theory. And that unification happened almost 200 years ago. And it really has continued to march towards that progress. Now, basically, everything that we understand about matter can be unified into one mathematical sentence, everything that we understand about it. The outlier is gravity. We don't know how to jam gravity into that mathematical expression. There are attempts, famous attempts, things like string theory, which are very successful and have certain attributes about them that people are thrilled about, but we don't have the complete picture yet.
So you mentioned gravity. I know that's one of the areas that you study. Mm-hmm. I'm Joe Layman, gravity, Newton, apples falling. That's what I know about gravity.
Yeah.
Tell me what you know about gravity. What's important for me to know about gravity?
So stringing together what you just said, we have this apocryphal story, the apple falls on Newton's head, and Newton writes down this beautiful expression. It is an absolute work of genius, Newton's theory of gravity. It's not that Newton was wrong. Newton understood there was something strange about what he wrote down. And that was, how is the Earth pulling on the apple? I mean, it's not touching it after all, right? How is the sun keeping the Earth in orbit? It's not touching it after all. He knew there was something strange about that. The way we think about gravity now since Einstein is that the Earth is not exerting any force on the apple. It's the stem of the tree that's exerting a force on the apple. The apple wants to fall under the natural curves in the shape of space-time that has been created by the presence of the Earth. And the apple will fall freely in the absence of forces if we let it, but we don't let it because it's got a little stem connecting it to a little tree. And so once the force is released, once that stem breaks, the apple falls freely along the natural curves in space-time.
You used the formulation, the apple wants to fall.
Yeah.
So I'm a literary critic, I'm an English prof. Personification.
We do that a lot with things.
So you're translating that for me.
Yeah.
Right? I mean, the apple doesn't want, or
right.
does it?
No, and so in fact, this is also a beautiful thing that we've known since Galileo. You know, the famous astronaut story on the moon where he's holding a falcon feather and he's holding a wrench, and some geological hammer, I don't remember which, and he lets them both go at the same time and demonstrates that they'll fall at the same rate. And we understand that now as saying they both follow the natural curves in space. It doesn't matter which one's heavier. And so when I say the apple wants to fall, I mean it will do as every other object would do, which is just follow those natural curves. The apple has no special curve of its own. It has the same curve the falcon feather has and the same curve the geological hammer has.
So you've talking about the moon. So your particular area of expertise is astrophysics. So what led you there?
It's so funny. I never thought I'd become a physicist. I was not that kid with the chemistry set, in the basement. And I thought physicists built bombs and did these terrible things.
Do that at least?
Well, only under duress, really, in fairness. Most physicists are pretty they're not warmongers, right? They're sort of airy, heads in the sky and dreamy. And I didn't understand that there was this creative side to being a physicist, and I was not interested in it at all, and I didn't know I was going to be interested in math. But I think I would have always known I was interested in astronomy. I mean, I remember being a kid on the beach late at night on a trip with my dad when there were no street lights on an island where there were no street lights. And I was a city kid. I grew up in Chicago, and it was the first time I had ever seen a dark sky, and in the southern part of the States. And it's so spectacular to see that view. And so I would have at any time probably in my life said that was interesting, that was amazing. And you wanted to jump into the sky like it was a pool, And I didn't understand that was an extension of theoretical physics, that theoretical physics is the study of the universe, and that is the universe on the largest scales.
Everything's an extension of theoretical physics.
Yeah, I mean, technically speaking, making this fabric is theoretical physics.
So you're highly regarded as an academic scientist. You've published scholarly articles on chaos, black holes, and gravity, but you're also a novelist and a writer of popular science. Why is it important to you to work in both science and the humanities?
I was always drawn to literature, always, long before I discovered physics. And art I was drawn to. And I thought for sure I would, study philosophy or become an artist or something like that. I don't think we're born one or the other. I just don't think we come out of the womb with this stamp on our forehead or with departmental divisions in mind. I think we're people and we approach the world and we're all curious. We all palpate things and figure out mechanics of things, and we all read books and think about the world and write narratives for ourselves. So it was not a matter of, wow, I'm going to do this radical thing and merge these two divisions. It was that I didn't ever really see the divisions in the first place. The divisions were artificially imposed on me. And it took me a while to, get the opportunity to just live out the other side of it.
Your career is this kind of argument for the view that these divisions are artificially imposed all over, right?
Yeah.
In a certain way?
Yeah, I think it's sad actually that my career is so unusual, because I can imagine a lot more people would be a lot broader, maybe not in the exact same way. I mean, even within theoretical physics, there's an incredible range of areas of expertise and people who are drawn to certain aspects of that field. It's what they're good at, it's what they love to do, and they carve out this natural path for themselves within this subject. I think it's a strange thing that it's so rare to step outside of those walls, because the natural path is very unlikely to be within those parameters.
You mentioned your attraction to art. You've collaborated with a number of artists on their work, and you were the first scientist in residence at the Ruskin School of Drawing and Fine Art in the UK. What connections do you find between art and science? What is it about art and science that resonates for you?
I can be very rigid on the divisions as well as on the similarities. So I am never confused which one I'm doing. I'm never confused that I'm writing a narrative book or I'm doing a calculation. And I know that those are two separate things, but so I don't think art and science are the same. And I think that that's not a productive even aspect of the conversation. I think what's fascinating is that science is fodder for art, and the artistic spirit drives some of the questions we ask in science, and it's just the sort of natural humanity of it. I do think scientists and artists think a lot about limitations and how the limitations, while that might seem constraining, but create for them a kind of playground in which they explore the world. So, famous artists who decide to use only light, like James Turrell or somebody like that. That is such a severe an intense constraint to use. And once it's in place, he has this incredible freedom and this ability to do something really tremendous. Whereas, you know, if he weakened the constraint, suddenly maybe the piece isn't as strong, the vision isn't as complete. And I think it's the same thing in physics. We have very rigid constraints, namely the factuality of mathematics and nature, but within that, you know, when the constraints are really rigid, there are these huge creative leaps. So Einstein accepts the limitation of the speed of light, and he discovers the relativity of space and time. I mean, that is a tremendous trade-off, right? A tremendous trade-off. We have that time and time again. Heisenberg's uncertainty principle is rigid constraint. Quantum mechanics. You know, Turing thinks about facts we can never know among numbers. Artificial intelligence. And I think that's an interesting similarity between them.
Wonderful. So you just mentioned Turing, so I'll turn to your most recent book, the novel Madman Dreams of Turing Machines, which tells the parallel stories of two key figures in the history of science, Kurt Gödel, the great logician and mathematician, and Alan Turing, the extraordinary codebreaker and pathbreaker in artificial intelligence. Why did you want to bring those two figures together in a novel?
I remember when I first discovered things about their personal stories, and I was just absolutely floored. So I knew about their work in various regimes, but I never knew about their stories. And when I found out some of those details, something about the extreme juxtaposition of believing that math exists outside of us, that the person who discovers the math does not matter, which I do believe, that if they hadn't discovered it, somebody would have, and if it's wiped out, somebody will discover it again. And I love that. But that at the same time, it was them, and that there's something about telling the story of the people who really did do it that is part of the history and the humanity of the experience, or of the subject. And so I tried to write a nonfiction book, and it just wasn't working. It just really wasn't working. In fiction, I felt I could play much more with the grander ideas, like they proved that there were facts that you could never prove to be true, but you could know were true. And that's a very broad stroke summary, but I felt I could play with that entire concept by writing a novel. Here are facts about these guys I can't prove to be true, but somehow this is a more true version of their lives than if I had stated just the biographical links.
Oh, you sound like a humanities person to me.
Exactly. So in my next life, I'll become a humanities professor.
So like all theoretical physicists, much of your work is mathematical. So what's special about the language of mathematics?
It's very reassuring, to be honest. I think because I started physics late by typical college-y standards, I did not feel secure about my physical intuition. I had no intuition for how things worked, but math I could follow from beginning to end. It's incredibly reassuring, and it's extremely elegant, and you can discover things you simply can't by just sheer feeling it out or intuition. It imposes facts on you that you would not have believed otherwise, really. And that is so, to me, exciting, to be forced to change your opinion, to imagine the world a certain way and be driven to accept that it's a different way by following the chalk, by following the math. I just thought it was so powerful. And I actually like the process of it. I like doing math. I know it's hard to believe, but it really is a pleasure when it's going well. When it's not going well, it's unbearably frustrating and humiliating, frankly, when you can't figure it out. But when it's going well, it's just this beautiful thing.
Among your interests is the topology of the universe. What is that? So
when we started talking about these curves in the shape of space, we started to think about space as a geometry. All of a sudden it's a shape. It's a three-dimensional shape. It's very hard to visualize, but it is a shape. We imagine the entire universe is this kind of curved space-time, that is what it means to be the universe. Not just the things in it, but the actual shape of space and time. And one aspect of that shape is how things are connected. And you know, this cup is different than a cup with a handle, which has a different kind of connected property. We call that the topology, the way that things are connected, and this counting of handles and holes. And you can have a whole origami of shapes. It can become extremely elaborate how things are connected and reconnected. And And that's just an aspect of the universe that we're just starting to really scratch at, figure out.
There is a kind of commonsensical idea out there, or popular science idea, that the universe is infinite. So how does it have a shape if it's infinite, right? I mean, shape implies there are boundaries or edges or something. So
right, this cup's not infinite.
Yeah.
It'd be really weird to try to talk about the shape of the cup if it were infinite.
Yeah, so what?
Well, maybe the universe isn't infinite. And Einstein thought about this right away. You know, he had this famous quip, which I often quote. He said only two things are infinite: the universe and human stupidity. You know, and then he adds, and I'm not so sure about the universe. So he had started to realize that once you start talking about space-time, you don't have to presume it's infinite. He did for a long time resist the idea even that it had a finite age. He wanted it to be infinite in time and infinitely old, and he had to come to the acceptance that actually his own theory predicted that the universe had a finite age, it had a big bang, it had a beginning in time. And once you start doing that, you could start to say, well, maybe it wraps back around and reconnects. And the Earth is like that, of course. The Earth is not infinite, nor does it have an edge. You don't walk from, here we are in Oregon, you don't walk towards New York City, go around the Earth, and fall off. You end up back in Oregon again. And maybe the universe is just like that. You travel on a rocket in a straight line, you don't turn left, you don't turn right, but you come back to the Milky Way galaxy again.
You study, among other things, black holes.
That's much more my recent work.
So what attracted you about them? Physics
Gravitational
joke.
attraction. Was that accidental? That was on
No,
purpose?
all
It's
planned. Yeah.
Black holes are the most fundamental aspect of astrophysics, in a sense. It's like talking about a fundamental particle in physics. They are objects that embody not just the most extreme forms of gravitation, but in some sense they're perfect. That black holes settle down to be these very idealized objects. I could make a black hole out of t-shirts, out of photons, out of antimatter, and they'd be identical. Okay, I can make identical black holes. There's nothing you could do to tell the difference between them.
So how do you make a black hole?
Well, nature has figured out one way. One
So
way
how does
is to collapse a very heavy star, and then the star collapses, and the matter forces which ordinarily resist collapse are unable to when it's run out of thermonuclear fuel. So usually it burns this fuel and that pushes it out. When it runs out of fuel, there's just not enough resistance and the whole thing collapses. It creates around it a curved space-time so strong that not even light can escape. And it leaves that indelible shadow behind it as it continues to collapse. So at the end of the day, the star that made the black hole is gone. It's not there at the edge, it's gone. All that's left is this shadow, and it's pure space-time. It's like a place, not a thing, really. And so it doesn't matter what made it in the end.
So it's like a place. It's
yeah,
not
it's
a
not
thing.
a thing. If you go to the edge of a black hole, there's nothing there.
So is it a hole in space? I mean, we call it a black hole. Is it literally a hole in space?
Well, that part we don't really know. We know for sure it's a shadow, and nothing can escape, and everything that falls in is in there forever. If you follow Einstein's equations all the way to their gruesome end in the interior of a black hole, it's a hole. And space-time stuff just sort of flies out of there, and we don't know what happens. Nobody really believes that that's the whole story. Okay, we would say, well, that doesn't sound very good. Probably this theory of everything that we're aspiring to unify with the matter forces will come in and explain to us what really happens there, but we don't have a handle on that yet. So it could be that there's another universe on the inside. It blows out into something called a white hole, and it creates a new Big Bang. And so the black hole looks, what, I don't know, 30 kilometers across from the outside, 60 kilometers across from the outside, but on the inside there's a whole universe.
Bigger on the inside.
It's much bigger on the inside than it is on the outside. It's like
Doctor
the Doctor Who.
So you mentioned it's like a shadow. So that's dark matter?
No, actually the shadow is simply because the light falls in and can't come out again. So if you put a black hole between you and some bright stars at some distance, it will just create a shadow on the sky.
So what is dark space?
People did wonder if dark matter could be accounted for by counting up black holes. Maybe they were black holes. So dark matter is just this proxy we have for matter that we can see affecting gravitationally things around it, but it's not luminous. There's no light. It's literally dark. And nobody knew what it was for a long time. It accounts for about 25% of the universe in terms of energy content, and people thought maybe it was black holes. We don't think that anymore. It doesn't hold up consistently. It seems like dark matter is some kind of particle we've never seen before. And we're trying to find it in Large Hadron Collider by smashing things together in Switzerland. But that is one of the greatest questions out there.
So tell me a little bit more about the work you do on black holes, this recent work that
Sure.
you talk about twin black holes?
Or colliding black holes.
Colliding black holes?
Yeah, really, we're very excited about asking what happens when two black holes collide.
Is that happening a lot of places out there?
It should be happening all the time, but they're two dark things colliding. And so there's no telescope in the world that could see that. And so we can look out with the Hubble, with all of the telescopes we have on the ground, with everything we've ever built, and we'll never see it. But what can happen is that the black hole's curving the space around it, but by this tremendous motions of these orbiting collisions, that the whole space rings around it, kind of like fish swirling on a pond create this ripples in the water. But in this case, water is space itself. And we call those gravitational waves. And there's a big campaign to try to detect those. It's not light. It is not a form of light. It is literally a squeezing and stretching in the shape of space. Right now, maybe a billion years ago, two black holes collided. And right now, we're sitting here and we're being squeezed and stretched slightly by that wave that's traveled a billion years since that time. And we just don't notice it. My hand's getting a little, but it's imperceptible. Turns out that the experiment over a 4-kilometer distance is trying to measure these deviations in space of 1/10,000th of the nucleus of an atom.
You said there's a campaign to detect them.
Yes, the experiment's called LIGO, I should name it.
So what's the idea of the experiment? How are you going to detect this stuff?
So you want to somehow detect the changing shape of space. And we talked about the apple falling from the tree. Well, when things are falling freely, that's when they're best measuring the shape of space. So if that apple started doing this on its way down, you would say, oh, something's changing the shape of space. But no change would be so great that you would notice it by eye. But what they do, and this is an idea that started with people like Ray Weiss and Kip Thorne and Ron Drever, they imagine hanging mirrors very far apart from each other. And the mirrors would be sort of free, at least in this direction. And the mirrors would tell you if the space was squeezing and stretching. And the mirrors would act, it's kind of like building a musical instrument that's picking up the plucking shape of a guitar string or a drum or something. So space is ringing, and these mirrors float on the ringing space. And if you can tell how much distance has changed between them, you can record the shape of space.
When you say space is ringing, do you mean that space is creating rings, or do you mean that there's a sound?
It's a good question. And this becomes a philosophical question.
Uh-huh.
I think I mean that there's a sound. So there's no air. It doesn't matter if this happens in vacuum. But if my ear was very near to colliding black holes and space was changing shape, it could pluck the mechanisms in my ear and I could hear the black holes ringing and I would hear a sound. And in fact, even in the absence of air, and in fact, in the control room of this experiment LIGO, they listened to the detector through speaker systems. Okay? It's not about taking pictures of the sky. It's about recording the shape of a changing drum. And in a sense, you're recording a kind of a latent sound. It's like how an electric guitar string is plucked. It doesn't actually make a sound. You need to build the body and you need to plug it into an amplifier and then you have a sound. Well, this experiment is like the body of the guitar and the amplifier.
So you said a drum. What's the drum?
So I'm mixing my metaphors between guitar strings and drums. So a guitar string is a one-dimensional shape that gets plucked. You can imagine a drum is a two-dimensional shape that gets plucked. Well, the universe is a three-dimensional shape that gets plucked. And so the finger pickers are the black holes. And other things like stars exploding and other things colliding and the Big Bang and all this mayhem. And they're the finger pickers. And the drum is the three-dimensional shape of space, or the multi-dimensional guitar string, to mix the metaphors. And then this instrument is like the body of the musical instrument. It is both scientific and musical. And it will record the shape of space and play it back to us as sound.
So I asked you that question and you said, well, that's really a philosophical question. and that's a fascinating moment for me because it raises the question of the question that English profs always ask their students, like, so what, so what? Why does it matter if the shape of space is this space or that shape, or if the universe is infinite? What's the philosophical significance of those kinds of very hardcore astrophysics questions? Why does that matter?
Yeah, I think that's That's an interesting question because there's no one-liner to answer it, but we all know it matters. So let's say we still thought we were at the center of the solar system. How does it matter? It obviously matters enormously. It was incredibly impactful to displace us from the center of the solar system, to put the sun at the center, then to put the sun away from the center of the galaxy, just in orbit way outside, and then the galaxy nowhere in the center of the universe. That all of these things shape how we view ourselves in the world now. They shape our entire philosophy, cultural attitudes, and impressions. But is that why Galileo pointed the telescope at the sun? It's not. He did it just out of curiosity, right? And the impact that it has is kind of unforeseeable to some extent, but he did it just out of curiosity. And that's why we do it.
Science, science. So we just have a couple of minutes left.
Yeah.
First question, we'll see how the time goes, but you've written 2 books. You've just described some of your scientific research. Any other books in your future?
Yeah, so I'm writing a book on black holes, and I'm writing a book about this experiment LIGO.
And are these books aimed at people like me?
Absolutely.
Or?
And you know, people ask me, why do you popularize science, or why are you interested in doing outreach? I don't think of it as either of those things. It's simply writing. It's writing a book. And I don't think if somebody writes a book and it happens to be about the Ivory Coast, that they're popularizing politics or cultural history. They're simply writing a book, and that's their material. And that's what I feel like as I approach a book. I want to approach it as a writer, not as somebody who's trying to educate people. I try to avoid too much expository stuff. I want it to be in the book, that it has, you know, it's an object of its own. And I love the story of this crazy campaign to do this insane thing. And I didn't mention when we started talking about it, but it's been in development for 40 years. You know, people's entire lives were spent on this insane machine. And it hasn't detected anything yet. It's not done. It's not finished yet after 40 years. And there's something about that that's like climbing Mount Everest. It's an adventure story, you know.
Well, on that wonderful final note, I want to thank you for sharing your adventure story with us.
Thanks so much for having me on.
I've been speaking today with our guest, Janna Levin, who is an astrophysicist and a writer. She gave a talk titled "From the Big Bang to Black Holes, Time, the Universe, and Everything." That's the Cressman Lecture, part of the Oregon Humanities Center's Connection series. The lecture was given on February 19th, 2015. Thanks again for coming on the show.
Thanks so much.
Thanks for watching.